Hello, this is Nicole Armand, and this is for Math 1350, Math for Teachers 1. And this is the recording of the video you're going to need to watch to make the foldable for Venn diagrams or sets. So let me zoom out a bit here. You need this piece of paper right here. Straighten it out a little bit. So I should have provided a handout for you already to make it. It is double-sided, and all you need to do is fold it in half, hot dog style. So you know how I like to have my edges all lined up. Well, I almost have it. Let's see. Okay. So on this front side right here, this is actually an example of a Venn diagram with some more content that we need to know, but we are going to go to the inside first. And I'm going to get out some of my colored pens that I also like. You can do the same. Get this up a little bit more. All right, so we're going to start out with some definitions and examples, and we're going to start off with a set, which is a well-defined collection of objects or elements, as they are called. And in order to denote a set, we use a capital letter. So set A, if we wanted to talk about that, would be an uppercase A. Okay, so now the next one is element, and it is a member of the set. So we use this symbol, which means it kind of looks like an E, a weird E, but an E anyway. And in set notation, it means is a member of. So it looks like this. So it's kind of like the word, this set contains this element. And then we have the same symbol with a line drawn through it that shows that it is not an element or not a member of. So I could say that set A consists of, and notice that I'm using curly braces to make a list of my elements, and I can put the elements in any order. It does not matter. Order doesn't matter for a set. And so A, B, and C are elements of set A. Okay, so far so good. The universe, which is a set that we denote with a capital U. Well, somebody keeps blowing up my phone. Put it on silencio. Even my VIPs can get through anyway. Here we go. The U is a big set, so it's a capital U. And it is thus the universe of possible objects or elements. So we say that an element E is either inside the universe or an element E is not inside the universe. And this is how we decide that a set is well defined, which I mentioned but didn't explain in the very first definition of set. Okay? So now the complement, which we denote as either A, so the complement of set A with a bar on top, or A with a prime on it like this, is the set of elements in the universe, so in U, that are not in set A. So if we were to draw a little picture of what the complement looked like, then we'll make ourselves just a tiny little Venn diagram right here. And we will make a circle to denote set A, and then everything that is not in set A but is in the universe, and the box represents the universe, then that would be everything else. So everything in the universe that is not set A, that is the complement. So it is not the kind of complement that you would be thinking of that's actually spelled a little differently that says, hey, you look nice today. Not that kind of compliment. Okay, so let's see, let's talk about A is a subset of B. That's what that symbol means. So this symbol is subset. And it means that every element, E, B, E, R, Y. Sometimes it's hard to talk and write at the same time. Every element of set A is also an element of set B. So for an example, if we said something like set A is X and Y, and set B is X, Y, and Z, then A is a subset of B. So we'll come back to subset in just a minute. Notice that B was a larger set as far as its cardinality, as far as how many elements it has. This second subset means that the two sets cannot be equal. So we call this a proper subset. And you can't have equality. So it's kind of like having the less than symbol as opposed to the less than or equal to symbol. Okay. So that means that there is at least one element in B that is not in A. Okay. Let's move across here to the empty or null set. This is a set that has no elements. And it is denoted as a circle with a line through it like this, or you can just put two curly braces next to each other like this with nothing inside it. And now let's add to this list the word cardinality. Which is the number of elements in a set. So if we look back to our examples of A and B right here, we put the letter N in front of A. The number in A, in this case, would be 2. And the number in our set B would be 3. The number of elements in the empty set is 0. Okay, so just to add another little note here, if you are given a set such as the set B, X, Y, Z, then you can make quite a few different subsets out of the set B. You can make all the sets that have just a single element. So you could have the set that only has X in it. You could have a set that only has Y in it, and then you could have a set that only has Z in it. Then you could have all subsets that have 2 elements in it. So you could have the set with XY, the set with XZ, or the set with YZ. Then you could have the whole set, the one with 3 elements, 1, 2, 3, X, Y, and Z. So when we're looking at a set, if we know its cardinality, which in this case we do because we can just count, there are 1, 2, 3 elements in set B, then the number of possible subsets is 2 to the n, where n is the cardinality. So let's add that. The number of different subsets of B is 2 to the 3rd, because the cardinality of set B is 3. So in general, it's going to be 2 to the n. So in general, is 2 to the n. Just squeeze that in there. So for proper subsets, since you can't have equality, then that means that the number of different subsets would be 1 less than these improper subsets that could have equality. So we'll add here that there are 2 to the n minus 1 number of proper subsets. Okay, so far so good. So now we're going to actually kind of move up the page this way. So the next thing we're going to do here is the union. And we're going to start drawing ourselves some little pictures. So the union is going to be all of the elements in both sets. The U, the symbol, is called the cup. Okay, so let's draw. Here's our universe. And sometimes we put a U in the corner there. We can have set A and set B. I'll use 2 different colors for it. And in this case, it doesn't matter if set A and set B, this is not a very good one. So if this is set A and this is, ooh, let's just throw things all over the place. Set B. So it really doesn't matter here if the 2 sets have any overlap. I have drawn them that way, but that doesn't mean that they would have overlap. Then the union is going to be anything that is in one set, the other set, or both sets. All right. Now we want to have a look at the intersection. And this would be the set of elements common to A and B. And the symbol, the upper or the upside down U is called the cap. So we have the cup and the cap. And we can draw our universe here and our sets. And the intersection is going to be what is common. So it's going to be this little football shaped thing right here. This is what set A and set B have in common. So in other words, it's what is in both sets. Now we have the word disjoint, which means that there are no elements in common to their intersection. So A intersect B is the empty set. So draw a little example. It's our universe. And then A be over here. And B will be over here. And there is no overlap. There is nothing in common. So the intersection of A and B for disjoint sets is the empty set. Okay, so far so good. Remember, you're watching this on your own to make this foldable so that you can have it ready so that during class we can actually work on problems that use these. But you can always ask questions when you get back to class if there's something that you don't understand, right? No problem. Okay, so now we want to talk about this last column, one-to-one correspondence. What does that mean? Well, you might remember that we talked about one-to-one correspondence way back in 1314 when we were talking about functions. And we were talking about functions and we were talking about, okay, if x is this value, then what value is y? We put in an x and we got out a y. We used function machines sometimes. And so basically it was an assignment. And if all the elements of x, of the domain, and all the elements of the range were matched up exactly one-to-one, we called that a one-to-one correspondence, and then it meant something special when we were studying 1314. So here, it means something similar. It is an assignment between sets. So suppose I have the set A, B, C, and I have the set 1, 2, 3. Then I could assign the element A in the first set to the 1 in the second set. I could assign the element B to the 2 in the second set, and I could assign 3 with the C. And this would be a one-to-one correspondence. So I'm going to make a list of a few sets. We're going to kind of scribble over these little greater than and less than signs here. And we're just going to write, so for example, set A is A, B, C. Set B is triangle, circle, square. Set C is 1, 2, 3. And set D is going to be X, Y, Z, Q. So each of these sets could have a one-to-one correspondence with the other sets except for set D. So set D cannot have a one-to-one correspondence because it has an extra letter. So the Q or the X or the Y or the Z, one of the elements in set D would be left without an assignment because we would run out of letters in the other sets. So what that basically means here is that if we could make one-to-one correspondences with A, B, and C, any of those with each other, that basically means that the sets are equivalent because they have the same cardinality. So we're going to say that equivalent sets have the same cardinality. So we can say that the set A is equivalent to the set B, which is equivalent to the set C, but not D. And we can also say that they match. So notice the difference here between equivalent sets and equal sets. When we use the word equal, then we are talking about two sets that are identical. They have the same elements. Except that the order does not matter. Okay. So I could say that the set X, Y, Z is equal to the set Z, Y, X. Because they have exactly the same elements, just not in the same order. Right? Finite sets have a cardinality that can be counted. So we could also say, we could use the word limited. So a finite set, an example might be the odd numbers from 1 to 10. That would be a finite set. On the other hand, an infinite set has a cardinality that cannot be counted. So, for example, the set of all even numbers. So we cannot count how many even numbers there are because that set is infinite. And just a note, by the way, the symbol infinity, which looks like an 8 on its side, is not a number. Okay, and the reason is because there's always a bigger infinity. That might seem strange, but if you ever start studying some higher level math and sets, or maybe even topology, then you'll learn that some infinities are bigger than other infinities, which really starts to make your head hurt after a while. For now, finite sets and infinite sets. Okay, so that takes care of the inside of our foldable for sets and Venn diagrams. So now we want to take a look at the outside, which is its own Venn diagram. And we have here the large rectangle, and we have here the universe, which says it is the set of real numbers. We have another box, or another just smaller disjoint set called the complex numbers, or the imaginary numbers. They are disjoint from the real numbers. What we want to talk about right now is our universe of real numbers. And then notice that we have some sets. And notice that they are all nested inside each other. That means that any number that is a natural number is also a whole number, is also an integer, is also rational, is also real. So the natural numbers are a subset of the whole numbers. The natural numbers are a subset of the integers. The whole numbers are a subset of the rational numbers. But over here, we have a disjoint subset called irrational numbers. And notice that there's no overlap between this largest circle, the rational numbers, and the irrational numbers. And that's because those are disjoint sets. A number is either rational or it's irrational. It cannot be both. They are both still part of the universe of real numbers, but they are not both. So let's start all the way on the inside with the smallest set. Okay. So the natural numbers are also called the counting numbers. What is the natural number to use if you were to start counting something? What number do we start with when we're teaching children to count? We start with 1. 1, 2, 3, 4, ... And the 3 dots mean that this goes on and so on, etc., whatever kind of wording you want to use. 5, 6, 7, 8, on and on. The natural numbers are an infinite set. Okay. The whole numbers are almost the same as the natural numbers. It has one more number in it, the whole numbers have, that the natural numbers do not have. Inside the whole numbers, we have 0, 1, 2, 3, 4, ... and so on. So the whole numbers have one element that the natural numbers don't have, and that is the 0. So we'll write a note. All right. The integers, on the other hand, look like this. ... -3, -2, -1, 0, 1, 2, 3, ... Notice that this set is infinite in both directions. So hopefully you can see what I mean, that even though the natural numbers, the whole numbers, and the integers are all infinite sets, the integers are still a bigger set than the whole numbers. So we have 2 different sizes of infinity. Yes, headache big time. Feel the migraine coming on. So we are talking about the positive and negative whole numbers and 0. And we talk about the integers. So we're going to write positive and negative whole numbers and 0. Okay. So far, so good. Now we want to move out of the integers, which are still whole numbers, and go to the rational numbers. Rational numbers can be thought of in a couple of different ways. They can either be thought of as decimals, and these decimals have to repeat or terminate. So repeating or terminating. And then we have fractions. So the thing that's important about rational numbers, and I'm going to show you some examples in just a minute. The thing that's important about rational numbers is that every rational number can be written as a quotient of integers. So we're using the integers to qualify or quantify the rational numbers. So how can this work, you might ask? Well, we can have things like negative 1.25. We could have 0.75. We could have 2.123 with a bar over the 1, 2, 3, indicating that it's 2.123, 123, 123, 123, where the 1, 2, 3 repeats forever, but still it repeats. Okay. So what I'm saying is that each of these decimals could be written as a fraction as well, because every rational number can be written as a quotient of integers. So if I wrote negative 1.25 as a fraction, that would be negative 5/4, for example, 1 1/4 negative. 0.75 could be written as 3/4. And I'm not going to use 2.123. I have no idea what that is as a fraction. There is a way to figure it out, but I want to just write another common fraction, which is 1/3, which can be written as 0.3 with the bar on top of the 3 repeating. Okay. So this set, the rational numbers, is also infinite, but it's a bigger infinity than the integers, because not only does it have all of the integers, it has all the numbers in between all of the integers. Therefore, it's a bigger set. Okay, so over here, you've got just a little box to talk about irrational numbers. Well, those are the ones that aren't rational. So we kind of use the rational numbers to define the irrational numbers, because those are numbers that cannot be written as a quotient of integers. So perhaps it's a decimal that does not repeat or terminate. So an example would be our friend pi. Pi has been calculated by supercomputers out to millions or perhaps billions of digits. There's a supercomputer working on it right now to try to come up with what the next digit is. But pi is irrational because its decimal places never end and they never repeat. Other irrational numbers would be things like the square root of 2. There is no number that one should square to get 2. So 2 is irrational. We estimated, it's like 1.14 or something like that. And there's something I want to kind of caution you about, because you're going to run into this depending on what grade you teach. If you use pi, just a little note over here. Here we go, throwing pins at things. So just a note, we use an approximation for pi because we want to calculate with it, and we say that it is approximately 3.14. You might come across, depending on what grade level, you might see that pi is also approximately 22 divided by 7. I don't like using 22/7 for pi because 22/7 is a rational number and pi is an irrational number. So that's why I wrote this little equal sign with the kind of swirly lines to mean an approximation. I want you to understand that even though when you're learning fractions and you're doing math, perhaps some geometry where you're using pi and you tell students to use 22/7, I want you to understand that it's an approximation and that there's no way that pi, which is an irrational number, can equal 22/7, which is an irrational number, is a rational number. So it can't be both. So these are just approximations to pi, right? There's another special letter that you learned about in 1314, Euler's number. His name sounds like it starts with an O, but it actually starts with an E, E-U-L-E-R, and it's a lowercase e, and you studied e to the x in 1314, and the natural log base e in 1314. And so e is another special non-terminating, non-repeating decimal. It's 2.7 something, 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 and then it keeps going forever. But what's interesting is that this irrational number is related to the Fibonacci numbers, which you learned about in class during, I think, lesson 1.3. All right. So the circles here, let's make another little note, but it's fine since we didn't start with the front. That's why I wanted to do all of the inside of this foldable first, so that we could come out here and talk about subsets and cardinality and things like that. So the circles in a Venn diagram represent sets, as you might have guessed from what we did in the beginning. So the circles represent sets. And this is a Venn diagram. Okay, so there we have our sets of numbers. Now on the back of this, we have just some little extra things to doodle on here. And if we look at like what do each of these diagrams of the different ways that the circles are drawn, not all of them have the universe box around them, but I think we could safely say that this one, A and B, is probably representing disjoint. This could represent union or intersection or anything having to do with sets. This one implies that B is a subset of A. And this last one is just the relationship between three different sets. So we have another little space here where we can do an example. So let's draw our first Venn diagram. We're going to be doing quite a lot of this in class. Now that you have your Venn diagram foldable already created, you'll be able to use it to work problems in class. So here it says out of 50 students, 14 are taking English and 32 are taking science. If 5 students are in both classes, how many students are in neither class and how many are in either class? So it's kind of an interesting question. Let's just draw our box here. We do need to know that the cardinality of the universe is 50. 50 students is what we're talking about here, right? So let's take a circle here and label it E for English. And then let's take another set and label it S for science. And then let's talk about how many are in each of the areas of these sets. So this part right here, that's going to represent English only, right? Because it's inside the blue circle, but not inside the red circle that represents science. Now this area over here is going to represent science only, because it would be in the pink circle or the red circle, but not inside the blue circle. And then we have this third area, the football looking area. And we know that that is the intersection from what we did before. And so that's going to be both. So what we want to do here is figure out what the cardinality is of each of these 3 areas of this Venn diagram. So the thing I like to fill in first are the ones that are in both classes. It says 5 students are in both classes. So that means that I am going to put use a pencil. That means I'm going to put a 5 right here in the middle, because there are 5 students that are taking both English and science. Now, it says out of 50 students, 14 are taking English, but I can't just write the 14 right here, because the 14 that are taking English also includes the 5 that are taking science as well. So if I want to fill in this section here, which is English only, then what I have to do is I have to take my 14 English only, or 14 that are taking English, and subtract the 5 that are taking both classes. and that's going to give me 9 that are taking English only. Same thing with science. If 32 students total are taking science, then that means if I cover up the English here, that this circle, this pink circle, in total, it has 32 students. 5 of them are already accounted for. So if I want to figure out how many are taking science only, then I'm going to say, what is 32 minus 5, which is 27. And now I can answer these questions. How many students are taking neither class? Well, how am I going to know that? Well, what is 9 plus 5 plus 27? That's only 41. But we said out of 50 students. So what does that mean? It means that there are 9 students that are not accounted for. It means there are 9 students out here in the universe that are not taking English or science. Now we have accounted for all 50 of the elements in our universe. And so we can answer all kinds of questions about these sets now. The ones that are taking English only are 9 students. The ones that are taking science only are 27 students. This question, how many are in either class? I'm not sure that I really understand what that means. I'm thinking maybe it's talking about the 9 and the 27 that are in either class, but not both, right? So if we kind of clarify this, but not both, then we can say that either class is 9 plus 27. So that's going to be 36. Okay, so we have answered all the questions, filled in the entire foldable. You can ask questions if you need to once you come in class, but I'll expect you to have this done when you come into class on the day that we study Venn diagrams. So that's all for this recording, and I will see you in class.